Today we'll discuss about JEE Men's 2016 paper Physics. How students, let us solve the next question. A satellite is revolving in a circular orbit at height h from the Earth's surface. So let us say this is Earth's surface. This is the center and this is the surface. At a height h above the surface, from the surface it is at a height h, and here a satellite, here the satellite is revolving with a velocity say v at h above, and this height is very less compared to this radius of the earth r. So the given is that h is much less than r. So that means the satellite is revolving very close to the surface of earth. So this condition implies you can ignore this value of h whenever it is required. The minimum increase in its orbital velocity, required, so that suppose now it is moving with v, so how much energy extra it needs so that the satellite could escape from the Earth's gravitational field. It's close to, so you have to find the increase in the orbital velocity. You have to see which one of the option is correct. We must know that if a body is at rest on the surface of the earth, the potential energy is minus gmm upon r, and the kinetic energy is 0. So this mod of this value is given as half m dE square. If an object is at rest on the surface of the earth, then it's required this much of kinetic energy on mod of this so that it will escape. So from here I write v half m v square is mod of this value, that is g mm upon r. Taking mod of this value, that gives you the binding energy. So basically this is the binding energy. So from here mm will cancel and v is under root 2 gm upon r. So this is the escape velocity that is required for the object which is placed on the surface of the earth and is at rest. Now this is the energy is in fact needed. So, and in our question it is given that the object is at height h, but that height is much less than r. So I can assume that it also requires this much of energy. Otherwise, for a height h, it should have been 2 gm upon r plus h, the root. For height h, above this, it should have been the case. Why? Because this is on surface, this is for at height. Because you have known that the total energy is sum of kinetic energy plus potential energy. If the object, suppose this is the surface of the earth, the object is at height h above the surface of the earth, the total energy can be written as kinetic energy is 0 if it is at rest, potential energy is minus gmm upon small r. Small r is the distance of the particle from the center of earth, which is equal to r plus h. So therefore if I substitute that, I will get gmm upon r plus h. Binding energy is the energy that is to be provided so that the body will not return back. This binding energy is the modulus of total energy. Now from here, if I take the mod of this, I will get G mm upon R plus H. So this is the binding energy. Because H is much less than R, so I will only write, if I take R common and out, from here it is G mm upon R into 1 plus H by R. Because this is very less, so H by R is much less than 1. So therefore, I can make it equals to 0. If I vanish this, then it becomes G mm upon R. So the binding energy is this much. And you know that when a binding energy is this much is required, if the binding energy equals to G mm upon R, then that is provided in the form of kinetic energy, this half mv square equals to G mm upon R. If the kinetic energy is equal to this, then that corresponding speed is called escape velocity. So this speed is escape velocity. Now, if I solve this, then I'll get V equals to under root 2 gm upon R. This may the energy you have to give so that it will not come back. Now, in this case of satellite, already it is an orbital velocity. It has already orbital velocity which is equal to under root gm upon R. This is the formula for orbital velocity. Obviously, here also we have neglected the height being very less compared to the radius of the Earth. Therefore, in place of R plus H, we have written only R. If you see from here and here, it is root 2 times more than this. So the extra velocity that you have to provide, the question is the minimum increase in orbital velocity required. So this is the actual orbital velocity with which it is moving. But if this becomes this, then the body will escape. So the increase in orbital velocity equals to this value minus this value. This is the extra thing you have to provide. That is under root 2 minus 1 into under root gm upon R, taking root 2 common and this. So from here I write that the increase in velocity needed is root 2 minus 1 times under root gm upon R. If I see the option, then no option is matching. This is root 2 minus 1 into something. So this is root 2 minus 1 something. Here basically this expression is expressed in terms of small g. Our answer is in terms of capital G. So we will convert this capital G into small g. We know that small g is gm upon R square. This is because this is we obtain from Newton's law of gravitation that if this is Earth and the mass is present here, then the mass of the Earth is m, radius is r. If it is placed very close to that, then this h can be neglected. So from these two, the gravitational force acting on this object equals to m into g, and that m into g must be equal to the Newton's law of gravitation, the g product of the masses upon distance square. So from here we know that g equals to gm upon r square. If I substitute this g equal to gm upon r square, in place of gm I can write g into r square. So from here if I substitute that, I will get root 2 minus 1 on the root of gm. This gm can be written as gr square divided by r. 1 r will cancel out. If 1 r will cancel out, then the remaining is root 2 minus 1 and under root of gr. This is the increase in velocity required. If I see the option, then the option number 4, which is root 2 under root gr root 2 minus 1 under root gr root 2 minus 1. So therefore, the option number 4 is the correct answer. This is the correct answer, and option number 4 is the correct answer. So option 4 is correct. This is the extra increase in the velocity it is required. Okay, thank you.